We are now recording. So we stopped here last week, right? This was the last play, pretty sure. So you have these motor neurons, right? There are these nerve cell bodies that are going to be contained in various places in your spinal cord. And the big take home is mostly upper body muscles are going to be kind of up in the cervical vertebrae. And then most of your lower body muscles are going to be kind of in the lumbar and sacral region. Okay. And so because of all of that, you've got a few things in your T vertebrae, but mostly it's up and down. And all of the motor neurons for every muscle, okay, for each muscle, all the motor neurons that connect to that muscle are in roughly the same location in the spinal. Okay. So that's good, right? Because they're all together. And so when you turn one of them on, it's very easy then to turn all of them on at roughly the exact same moment in time, right? There's not going to be any sort of delay, right? Which, if you're a squirrel trying to get away from a cat, it's probably useful, right? And you touch a hot stove and you got to pull something away. You want to be able to turn all of your bicep or all of your plantar flexors or something on right now at the same time. You don't want to have some in the cervical, like, okay, those are on, but now I've got 500 milliseconds of delay to get it down the spinal cord. You know, if some of them were up here and some were down here, then you've got this sort of electrical delay that's going to occur in between. That's part of the usefulness of how we have things organized. So there are a couple more kind of pictures that I have in here. Maybe it will go forwards. I don't know. There we go. Okay. And just another way to visualize them is if you kind of think of them, right? Here's L4, here's S2, so kind of somewhere in here that you've got all of the quadriceps motor neurons kind of in this sort of 2 region that's going to be here, right? And they are proximal to the TA, they're proximal to the plantar flexors, right? Weirdly, they're proximal to the glutes and those kinds of. Okay, so that's kind of how things are organized. I'm not going to ask you any questions specifically about, right, where are the motor neurons for the hand muscles or where are the motor neurons for the tricep. You don't have to know, okay, well, these are at C5 and these are at C6 or anything. But I want you to understand and appreciate the kind of global anatomical structure, because that helps us impart function when we figure out, right, like all of our steps and our signaling pathways, right? They're all in the same place, which is good because then there's 14,000 other steps that have to happen as we're going to move along. Okay. I'm sure you guys have had this before. I'm sure of this, but I want to reiterate, okay? Because it will become more important and more meaningful probably on Wednesday of next week when we talk about sensory motor integration, okay? There's an orientation to the spinal cord. So there's an orientation to your vertebrae, right? We have the dorsal side and we have the ventral side. Now, always remember this, right? At least for me, sharks have a dorsal fin. It's on their back, it's on the outside. So dorsal is sort of the back, ventral is the more interior side of the spinal cord, okay? And within all of that, inside, right, of the vertebrae, you're going to have the area where there is the spinal cord, and then you're going to have this sort of other area that is here. And we're going to get motor neurons, okay? Motor neurons, for the most part, are on the ventral side, or the inner side of the spinal column, okay? Whereas sensory neurons are going to be on the dorsal side. And what I want you guys to note from here is look how close to each other they are, okay? So these sensory neurons, things that sense touch and heat or cold or position, are going to come from the periphery into the spinal cord. They're going to come in on the back, but they're very, very close in proximity to the alpha motor neurons that go to those same body regions, to those same muscles, okay? This is important because there's going to be signaling that occurs among those individual neurons. There will be sensory information that comes in that will have an influence then on how easy or difficult it is to activate these motor neurons that are going from here. Okay? And I know you guys have seen all of this before, right? What you're going to get basically is they each come out of either side, and then once they get outside of the spinal column, they're going to leave sort of from the bones, they're going to leave out of the foraminal space, and then they're going to basically, these axons are going to bundle back up together and run out to the periphery. It's this bundle of the spinal nerve that becomes these axons. These are what we think of. Those collections are what we typically think of as the nerve that you see, right? When you're actually anatomically dissecting someone. If you look here, you're looking at the ulnar collateral nerve or something that's down here. What that is we see it as a nerve, but that nerve is actually a giant bundle of axons from sort of the afferent receptors that are down here in your forearm and hand, and the axons from the motor neurons that control the muscles that are okay. Anybody else, when you did the cadaver dissection, you see the nerves and think, how do we ever like not just rip them in half all the time? They seem so small and so delicate. And then think of all of the things that you've done in your life when you've like had a bike wreck or you've fallen down or like whatever it is that my daughter does like every 5 seconds. And you're like, how do we not just shred those things all the time? But we don't. Okay. So this again is anatomy, right? Structure, and it's going to help us impart some of the level of function that we have that we'll see coming down later on. Okay. Our ability to integrate information that comes in and then adjust and control efferent motor output is 100% key to walking, running, life, like everything. Okay. Because you can do fun things. Okay, we'll talk about it next week, but I can do fun things. Anybody ever had a nerve block? Anybody ever had like surgery or something done and had a nerve block? A couple of y'all? What did it feel like to have a nerve block?
I just felt a lot of pressure.
Okay. After you had it, because you could sort of move around a little bit, but you don't feel things very much, right?
Yeah.
Depending upon what they're doing. Okay. There's a group at the University of Utah in the medical center, and they have an anesthesiologist, and they will come in, and this is going to be kind of a weird buzzword. You guys know what fentanyl is, right? You guys have heard of fentanyl? Okay. I'm not going to ask some of you how you might know what fentanyl is or anything else, but they inject fentanyl into these neurons. And so you don't feel things, basically. You still have full motor output, but the fentanyl inhibits those neurons on the dorsal side. And so you have very little ability to process information coming in from the periphery. They do that, and then they have people exercise. And they just tear ass out doing things. And they have no sense of how hard they're working. They have no sense of pain and these other kinds of things. And they go out really, really hard, and then they die, basically. And they die and they fatigue really, really quickly. It's fascinating because they can study then our ability to kind of make these slight adjustments and judge based upon this input coming from the kind of the afferent side of the nervous. Okay, so again, we'll talk more about this next week. We'll talk about how these things signal back and forth to each other, what the different kind of peripheral receptors are for those things. But again, I just want to show you guys some of this so that you can see it. Okay, we talked about almost all of this last week. We talked about myelin. I will mention, right, one of the issues with myelin, this sort of fatty covering that is along the axons, is it originates from cells called Schwann cells. Okay? Maybe a thing of my generation, anybody, I always think that we had these guys that drive their trucks around, they called the Schwann fan, and they would sell like orange sherbet push-ups and frozen things that they would drive around there with like the ice cream man, and they would sell stuff. Before there was HelloFresh and all of these things where you could order food. But that's what this makes me think of. But you have Schwann cells, and then they produce this myelin, which is these fatty lipid layers, and it wraps itself around the axons. And then at the nodes of Ranvier, we're going to have very, very high concentrations of sodium and potassium channels. which then, in essence, it's not how this works, but it in essence allows action potentials to jump from node of Grandier to node of Grandier, and that jumping process speeds up conduction. Okay, it speeds up conduction. And that's the big thing. This process of speeding up conduction on the axons with the myelin is called saltatory conduction. Okay, saltatory conduction. There are pathological conditions, as I mentioned last week, where if the myelin gets damaged, okay, you lose myelin. Multiple sclerosis does this. Okay. There are other conditions where you have autoimmune things where the immune system attacks the myelin and it makes it go away. Myasthenia gravis and some other things, and it slows nerve conduction velocity down, and it affects people's ability to move. Okay, so that's what's going to go on. What's going to go on there? Okay. So the next thing that we're going to talk about in quite a bit of detail is something called the neuromuscular junction. Okay. The neuromuscular junction is the area that is oftentimes referred to as a synapse. Okay, where one part of the nervous system makes contact with whatever it's trying to signal to, we oftentimes refer to that as a synapse. Okay. So the special synapse that occurs at the end of an axon or a motor axon where it is going to come into close contact but not actually touch individual muscle fibers is called the neuromuscular junction. Okay? On the nerve side and on the muscle side, there's some very special structures that are there. That I'm sure at this point you guys are getting tired of this, but those special structures help us have the correct function at this. And that function is going to be very fast, okay? Very fast sort of signaling, but also very, very fast turning off of the signal and non-wasteful signal, okay? We don't waste neurotransmitters. Because here's a bundle of axons, they're coming all the way down here. These are individual muscle fibers. And then this area right here, right, this is where the neuromuscular junction is going to be. If you read neuroscience books, they refer to kind of the end portion where the motor neuron comes down and it gets close. Rather than calling it a neuromuscular junction, they call it a motor end plate, which is the same thing as just a neuromuscular junction. But this is maybe here, the junction may be 3, 4, for those of you that are very tall, unlike me, 5, 6 feet from where cell bodies are in a spinal cord. And so that's a long way if you have to make neurotransmitters in the cell bodies of spinal cord and then move them all the way down, okay? It's a very long way. It takes a very long time. It takes a lot of energy. And so one of the reasons that we have this specialized structure is so that we don't waste neurotransmitters, because it's the cost of the bunch to get them down. Okay, so we'll talk now in some level of detail about what's going on the nerve side and what's going on the muscle side and why it looks in some ways the way that it does. Okay. Okay. So 2 things to keep in mind. 2 things. 1, surface area matters. Okay? Surface area matters. So when you look at the structures on the nerve side, we're going to have this area where one axon comes down and then it splits, and there's going to be multiple kind of little motor end plate pieces that are going to come off and form multiple junctions. That's going to be there. Having multiple gives us more surface area. Okay, it's like having 5 fingers instead of 1 or something. Okay, better close contact, better transmission. Also, you will note on the nerve side that each little place when it gets close to the muscle fiber is going to kind of bulge out and around. It's kind of like a light bulb. Okay, that special area is called the bouton. B-O-U-T-O-N, bouton. All that we're doing here is increasing surface area again. Okay. More surface area means more area, more surface, more places to be able to release our neurotransmitter or release acetylcholine and get it hopefully to get across and get signal onto the muscle. Okay. That's what's going on here. Okay. So you will note it comes down, it bulges out, here's the bouton, right? In this region, you can see there's some mitochondria and things in there, but we're also going to have several specialized receptors, okay? And then we're going to have all of these little vesicles that are in here like this, and in these vesicles is our neurotransmitter, which is acetylcholine. Okay? So the way all of this works is increased surface area on the nerve side. We've got more area to hold our acetylcholine, and then more ability to release that acetylcholine onto the muscle side. Okay. On the muscle side, you will also note that here, that the sarcolemma is folded. Okay, it's folded in the area right under the nerve. This is just like in your small intestine, right? How your small intestine is folded. Or it's in some ways the same function of having all of those alveoli in your lung, right? What it does is it increases surface area. So the nerve side maximizes surface area so it can hold its neurotransmitter. The muscle side maximizes surface area so it can have lots and lots and lots of receptors for that neurotransmitter. Okay. So the green little things that are going to be here, some of them here are going to be, these are acetylcholine receptors. Now down here, these are going to be sodium potassium or voltage-gated sodium channels, I believe. But that's what's going to happen on this. Maximize area so that when we release any acetylcholine, there's a great chance it's going to get bound up and transmit our signal. Okay. Again, structure, parts, function. Okay. We want to be able to turn a muscle off as well as turn it on exactly when you want to. This is going to help us to do that. All right. So on the muscle side, okay, this space here, you will note very, very clearly, you will note that the nerve does not make physical contact with the muscle, which I've always found kind of weird, but it doesn't, okay? It doesn't. So this sort of upper portion, the more proximal portion of the space between the two things here is called the primary neuromuscular cleft. And then inside of the folds on the sarcolemma is called the secondary neuromuscular cleft. Okay? And again, the purpose of this is to have lots of surface area, lots of sarcolemma where we can put acetylcholine receptors. Okay? There's another set of structures, though, that are going to be associated in the clefts. And it's kind of denoted here by this thin little line that you can see. And so there is a basement membrane on the side there. In that basement membrane, one, it provides structure, but also it contains an enzyme called acetylcholinesterase. From your neurotoxin assignments, anybody know what acetylcholinesterase is supposed to do? Okay, how does it drive the reuptake? What's it got to do first before we can reuptake it? Oh, that's right. Acetylcholinesterase is going to break acetylcholine away from its receptor. Acetylcholinesterase and the basement membrane are what turn off signal from the nervous system to the muscle. This is the first place where we initiate termination of a muscle contraction. Okay? So if you do something that makes the acetylcholinesterase not function correctly, you cannot turn off the contraction. And then you just have a cramp. You cramp until you can't shut it off at all. Then that muscle gets tired, and then God forbid that muscle is your diaphragm, then you can't breathe. Okay. That's what's going on here. We have our basement membrane, we have our acetylcholinesterase, right? Once acetylcholinesterase breaks acetylcholine off, then we're going to sort of suck the acetylcholine back into the nerve side and try to repackage it back into our vesicles. Okay, that's what's going on. Questions about that? Nobody? Okay. Okay. Let's talk about a motor unit. Maybe one of my favorite things in the world to talk about. And I apologize for that. A motor unit is, okay, a motor unit is one motor neuron and all of the muscle fibers that it connects to. Okay? One muscle fiber and all of the things that it connects to. Okay. Let's sort of do an example of something. I don't know. My folks in the very back row, right? My three guys. Can you all stand up? What are your names? Dylan. Jamie. And then Brittany. Okay. You guys are a motor unit. I got one motor neuron and I got two muscle fibers. Okay. So when one of you moves, go this way, then you guys go with it. Okay? That's how a motor unit works, right? So if the motor neuron goes jump and does this, then you guys jump. Right? So jump. So we do this. Okay? This is how the nervous system, thank you guys, y'all consider. This is how the nervous system works. Okay? Now, that's one. Okay? Most muscles have hundreds or thousands of motor neurons. And so they're all set up different. So that would be a small motor, one motor neuron and two fibers. But then I could have said everybody else over here on this side of the room, we're going to have a motor neuron and six fibers. So a bigger one. Okay. And as we will talk more about on Monday, more fibers that are connected. And when that motor neuron sends a signal down and it turns them on, they all turn on at the same time. They all do the same thing. More fibers, more cross bridges. Cross bridges, more force. So we use this particular setup. We use our ability to turn on and off individual motor units to help us control force production. Very, very tightly. Okay. There's this very orderly process in which they get turned on. Why these ones instead of others? We'll talk much more about that. Okay, as we go forward. That's the general idea. Okay. Every motor neuron connects to many fibers. Every fiber only connects, or should only connect to one motor neuron. Okay. That way you're not going to get crosstalk and things that are gonna go on. So here would be, right, a small motor unit. Here would be a larger motor unit and kind of how it is all set up. Okay. The smallest motor units in your body may only connect to 10 or 20 or so fibers. Very small motor units in your hand muscle, in your eyes. Okay. Then you're going to have some, like ones in your quads, that may have tens of thousands of fibers that are connected to one motor neuron. It's very, very large, very giant kinds of motor units that have an ability to generate a huge amount of force compared to. Okay. We'll get into next week why some muscles have lots of small units, why other muscles have some small and some medium and some great big ones, and why that's going to kind of help us determine the general function of those muscles. In a very general sense, big, strong muscles that we use to walk or run or jump oftentimes have very large motor units because their purpose is just generate lots of force. It's a gross motor movement, right? Whereas small muscle that you use to write and in your hands and your face to make these very subtle movements have lots of small ones because it lets us very finely tune the amount of force that we generate. Okay. Cool. Checking my time to make sure we have time to go through our other things. Okay. What's an action potential? It's electricity. Okay. If it was later in the winter, we could all do one of these things, and then you could like shock your neighbor or something, or yourself, like scrape your feet around. But that's what an action potential is. It's just electricity. Okay. It is a brief electrical signal that's going to move or get propagated. We use electricity to signal throughout our body because it's fast. Okay. It's very, very fast. Okay. I can send electricity from this side of the room to the next to this side of the room in like hundreds of a second. Whereas if we had to physically have you guys make a chain and like touch each other, boom, 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 much, much slower. Okay. That's why we use all of it. Our brain, all of your thoughts are just action potential. All of the things that you see in this room are just action potential. Okay. There are electrical signals generated in the brain from these different receptors that we then sort of put together to make things look the way that they look, or to make things feel the way that they feel. Okay. Right? When something hurts or something feels sharp or soft or hot or cold, all that is electrical signals that the brain interprets as a certain thing. It's kind of a wild concept. Okay. That's what we're getting. The thing that I need you guys to understand is in order to get an action potential, this is going to be key for the nervous system and it's key for muscle fibers. Cells must have a resting membrane potential. So what the hell is that? A membrane potential is a difference in electrical charge from inside to outside of those cells. Okay? From inside to outside. More positive ions on one side, more negative ions on the others. And so we need that because if there's a difference, then we can flip that difference around and get electricity. Okay? So nervous system cells have a resting membrane potential. It's usually about minus 70 millivolts. It's a little more negative, okay, on the inside than the outside. Same thing goes with muscle fibers. About minus 70. Okay. Part of the resting membrane potential is going to be due to concentration gradients where there's a difference between positive and negative ions inside and outside, and a difference in the amount of certain ions. Okay. We typically will use sodium and potassium as the big ions that will move when we get an action potential. And so we have a membrane potential and we have a concentration gradient where there's a lot of sodium on one side and very little on the other. Okay? Or there's a lot of potassium on one side and relatively little on the other side. Without those two things, no action potential. Okay? So if you get a neurotoxin that messes up the concentration gradients, right, or prevents certain channels from opening to allow the concentration gradients to do things, then no signal. If I give you some sort of anesthetic, right, be it topical, local, or general, I can do the exact same thing. All we're doing, anytime you like go to the dentist, they give you a shot, they numb you up, you get one of those things, you get a nerve block, whatever it is, all they're doing is just preventing the generation of action potentials, right? And so then the nervous system can't communicate. So you either can't turn a muscle on or you can't feel whatever, you don't interpret the input on one side as being painful or non-painful or something. That's what goes on. That's the cool thing that happens with everything with action potentials. Okay. Here you're going to have sort of the differences, right? Generally, in a nerve cell or in a muscle cell, outside of the cell has more positive ions, inside has more negative ions. That generates our negative membrane potential. And when we get an action potential, what generally happens is we let these positive ions come in. We go from being negative to positive, boom, electricity, signal, here we go. Okay. Okay. With our cells, with nerve cells and muscle cells, generally sodium is very high on the outside, relatively low on the inside. Potassium is very, very high on the inside, relatively low on the outside. Okay, and then there are some smaller things. There's a pretty big gradient for chlorine, chloride ions, and a little bit of a gradient for calcium. But it's really sodium and potassium that are the very, very big. Okay. Nerve cells and muscle cells are generally impermeable to sodium and potassium, or at least selectively permeable. What that means is I can inject around your cells a bunch of sodium, and it's not all going to just immediately go into a muscle cell. It will stay outside because there's no way for the sodium to get into or through the membrane of that nerve or the membrane of that muscle fiber. Okay? And so we get action potentials because in order to get them through, there are channels. There's doorways, if you will. And we will open those doorways at certain times. When the doorway is open, then things will diffuse down their concentration grade. So in some ways, we get an action potential. It's kind of like we're having a fire drill. Right? The doors in the back are closed. Let's assume that they're locked. You guys want to get out of here. You can't because the doors are locked. You guys are all sodium ions. Okay? And you can't get out. When we open the doors, right? There's lots of you in here. There's nobody on the outside. The doors are not open. What you want to do is get away. Like me at the football game this past weekend. Down in the concourse, there's lots of fucking people around. It's hot, we're sweaty, there's a lot of drunk people. It's not the best place to be, especially not with a toddler. You're like, what I want is to get away from all of these people. Doors open, the channels open, sodium ions are going to go from high concentration outside into the inside. But then now there's people, and there's sodium inside the cell, and that changes our membrane potential. That's how we do that. Now, once that has happened, our membrane potential is gone, and we have to get it back. Okay? Because we need another action potential. And so we have to then have a way to rejigger our membrane. You guys go out, well, then maybe there were people on the outside with potassium ions. And they're like, we don't like it. Now there's a bunch of y'all outside. We want to come in. Then it goes to the direction and it can restore our membrane. Okay? So we have selective channels that let sodium through sometimes and let potassium out at other times. And we use those two things to swap those ions around and control our membrane. Okay? I assume you guys have had this before. You guys had this in human phys or something like that, or intro to biology. If you really want to know and understand this, go to the biomedical engineering department and take a class called quantitative physiology. It may be the single worst thing in the entire world. And I'm a physiologist who likes math. Math always made sense to me, right? Chemistry made sense because chemistry is really just math. It's balancing equations and stuff. In quantitative physiology, you do the math of all of this, right? You do the math of all of the channels and this, it moves this much at this point, and what's the decay curve and all of this stuff. We get a lot of biomedical engineering students that come and take our graduate classes. And so they're always like, you mean we don't have to know and like do all the calculus and the derivatives and shit to figure this out? I'm like, no, just like know that it moves. And they're like, oh, praise God, thank you. So if you want to know, one of my best friends in the world, he is a biomedical engineer, right? And he teaches quantitative physiology, and I'm just like, you're a crazy person. With all of this. That's what's going on. Okay. So I want you guys to know this. These are just the regular steps in an action potential. We're going to get what's called a graded potential. You get a little bit of a change, in membrane potential, a little bit of a signal, and then it reaches some threshold change in membrane potential. And at that threshold, all the sodium channels open. They're called voltage gates. When the voltage gets positive enough, then boom, all the doors open, out goes the sodium. Or I guess in comes the sodium. That then makes the inside of the cell go very, very positive, and you get this spike. That's our action. Then we've got to close the sodium channels. We're going to start pumping potassium out to get ourselves back down. And then once we get down here, we're gonna overshoot a little bit, that's called hyperpolarization. And then we have to restore our concentration gradient, which we use a thing called the sodium potassium polymer. Okay. You spend, depending upon how active you are, if you just laying around all day, somewhere between maybe 20 to 30% of your energy expenditure every day just occurs for what happens out here. ATP to run the sodium and potassium pump and repolarize after action. Okay. And all this happens in such a tiny, tiny fraction of a second. I've sent thousands of action potentials. Just think about what I'm going to say to you guys and then say it and move on. So this happens really, really fast. We're really, really good at this. Okay. Okay. Now, I love this graph because I feel like it kind of lays over what's happening electrically. You can see kind of the time sequence of when the channels are going to be open. So in red here, right, or crimson, whatever you want to call it, this is probably more Arkansas color than OU color. Here is the change in membrane potential. But then in purple, what you can see is when the sodium channels are going to be open and when the potassium channels are going to be open. So what you will notice that, right, as this happens, both channels open, but the sodium moves really, really fast, and then it begins to come back down, whereas the potassium moves slower, but it stays open longer. And so positive in, then we're going to get positive out, and that's we're going to get this big switch, so the inside of the cell becomes positive, then we start moving out positive ions, and the cell becomes negative. Okay. That's going to be what we're going to call conductance or whatever, but I just want you guys to appreciate again when these things are going. Okay. Two things to remember here, and then we'll start talking about our signaling stuff. Something called the absolute refractory period and something called the relative refractory period. There is a very small window of time, okay? Very, very small. When after one action potential has gone, that you cannot get a second action potential, no matter how much input the nervous system gives from one neuron to the other, or from a neuron across the neuromuscular junction. Okay? The absolute refractory period is how we describe that period of time, right? It's thousandths of a second. It's a very, very small period of time. But the reason you have one of these is while the sodium channels remain open, okay? While they remain open as this is starting to come back down, we cannot get another action potential. You have to have the sodium channels closed, okay? And we have to begin to redo and make more sodium outside than inside, or when you open them again, there's not going to be anything to be able to see. Okay, that's the absolute refractory period. There is then another slightly longer window of time while the cell is repolarizing that is called the relative refractory period. And during the relative refractory period, the sodium channels are closed, but the potassium channels may still be open, but we can get another action potential. Okay, but the input from the nervous system to make that happen is larger than what it is in a normal resting state. You really got to want it during the relative refractory period. Okay. So this again helps us describe periods of time between action potentials, and it all is a function of which channels are open and when. Okay. The reason that an absolute refractory period is important, okay, is it provides on both the motor and on the afferent side, it provides us with one-way induction or one-way signal. We're not going to get signals going in both directions. Okay? A signal starts and it moves from the motor neuron out down its axon towards the muscle. And so what happens is, as the action potential jumps along, it polarizes, and then that patch of the axon or that patch of the sarcolemma enters its absolute refractory period. Then the action potential moves to the next piece, and the next, and the next, and the next. So what happens is immediately behind where the action potential is, we're in the absolute refractory period. So the potential only can move in one direction. It can't go back up in the other direction. And so that's really important so that we don't get our signals crossed and we don't get things going in the wrong way. Okay? And so that's in some ways the importance of these two tests. You all never think about this. The absolute refractory period generally never has any actual impact on our ability to turn on a muscle or our ability to use our brain or any kind of neurons. It's just a thing that exists and it's so short that we can't even really conceive of it, but it ensures one-way signal. Okay. Let me see what else I've got here. All right, we talked about, we're going to get this and our other things. Yep. Okay, cool. All right. Here's what I want you guys to do, okay? We're going to take about 12 minutes. 12. And what I want you guys to do is, if you turn your assignment in online, great, pull it up, okay? If you have it, like written on a piece of paper or something, also great, get it out. I want you guys to get into groups of about 5, okay? Or in essence, sometimes just those of you that are kind of around you is probably going to work best. People sitting in front of you, behind you, and share. Look at each other's and see what yours looks like in comparison to others. And then we'll start moving our way through and talk about what is this signaling pathway going to be. Okay. That will be our jumping off point for all of this. All right. So I'll give you guys about 10 minutes to share, and we'll spend 15 minutes or so trying to. Back on. All right. Who wants to start? Where do we start? And should we bring people up and be like, you are the motor cortex, and then you're going to touch over here. And then you should touch your right? Where do we start? Motor cortex. I had lots of questions about that. Like, what happens after the motor cortex? Because there's no information in the notes about all of that. Next phase. Okay. All things that don't actually all start in the motor cortex, you have premotor cortex, and you got to think about moving before you actually move, and then we've all kind of gone cross-eyed, and it's like, don't think about time travel. Okay? Motor cortex. There are neurons in the motor cortex in your brain, okay? In your motor cortex, they generate an action potential. Those action potentials are going to send a signal to adjacent neurons. And it will go ping, 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 eventually getting down right through the brainstem into the spinal cord. Neurons down spinal cord, action potentials down the spinal cord until we reach the alpha motor neuron. Okay? Everybody have that, right? My group over here was very concerned about, are we going to get an actual key to this to study from? You guys have all the right sorts of things, okay? Motor cortex, action potential signals to the spinal cord. Spinal cord, action potentials signaling down to the alpha motor neuron. Okay? We haven't really talked about this, but there is a structure on the alpha motor neuron that's going to gather those action potentials that are coming down. You guys know what that structure of the alpha motor neuron is. Dendrites, very good. Okay. Action potentials are sensed by the dendrites. They're going to send a signal to the cell body of the alpha motor neuron. That initially generates what we had just shown before, what's called a graded potential. A little bit of a signal, we get a little bit of a change in membrane potential in the cell body. Just a little bit, okay? Initially, that may not be enough to reach that threshold of -55. If there's a big enough signal from coming down the spinal cord big enough signal picked up by the dendrites, cross threshold, and we get an action potential at the alpha motor neuron. Okay, that then is transmitted down the axon. The axon has some special structure, right? What is on the axon that helps us move this action quickly? Myelin, very good. In the places where there's not myelin, what is that called? Nodes are on the edge. Very good. Okay. Down those two things, those special structures help us increase conductive velocity. Good. Okay. We've now moved our action potential out of the spinal cord. It's flowing down an axon towards the muscle that we want to contract. It's going to reach the end of the axon. Okay? The end of the axon, which we could call the motor end plate, we could call it the neuromuscular junction. If you want to be really uber specific on the axon end, you can call it the bouton, the place where it kind of bulges out into the lightning. Again, it's in the notes for Monday's lecture, but when the action potential comes down and it reaches the end, there are some specialized channels that are going to lead from the axon out towards the neuromuscular junction. They're called voltage-gated calcium channels. Okay? As the action potential moves, they activate or open up the voltage-gated calcium. That lets calcium come in on the nerve side. In the bouton, calcium comes in. That calcium signals for all of those vesicles, or some of those vesicles, to dump what into primary and secondary blood? Acetylcholine. Okay. We have now gone from an electrical signal to a physical signal, right? Action potential very fast. We now have a physical neurotransmitter signal. Through the primary and secondary cleft, the acetylcholine floats, okay? And by random chance, it's not that random, but it is still chance, okay? It will bind, hopefully, to what on the muscle side, on the sarcolemma? Acetylcholine binds to the acetylcholine receptor. Okay? We know a lot about the acetylcholine receptor. Very highly studied. Outside of the insulin receptor, it's about the most well-known receptor that we have. Okay? It binds there. Physical signal. Now we're going to go right back to an electrical signal. Okay? Acetylcholine binds, and that opens sodium channels on sarcolemma. Sodium moves in, voila, new action. So, electrical signal in the nervous system, physical signal to cross the neuromuscular junction, electrical signal again along the surface of the muscle. Okay. Action potential moves out from the junction, then along the sarcolemma, and it's going to come to a tunnel, basically, that will take it from the outside to the inside. What's that tunnel? T-tubule. Good. It goes down into the T-tubule, and it will then activate a receptor in the T-tubule that is very close to the sarcoplasmic reticulum. What is that receptor? Dihydropyridine receptor, DHP receptor. DHP gets turned on. DHP connects to and opens what receptor in the sarcoplasmic reticulum? It's like pulling the cork out. Okay, what is that called? Ryanodine receptor. Okay. So we've now gone from an electrical signal along the muscle surface down into the fiber and the T-tubule. Now we're going to go back to a physical signal. Ryanodine receptor gets opened, calcium flows out of the sarcoplasmic reticulum. That calcium now is just going to, in some ways, imagine it's just like, I'm gonna open an air freshener up here or spray, I don't know, we'll spray some Axe body spray. Right, like up here in the front of the room. And it will then just diffuse out into the room, right? Muscle fiber is like that. It's gonna go out into the room, and that calcium will hopefully bind to what structure? Oh. It binds the troponin, changes the troponin shape. That pulls tropomyosin out of the bindings, the myosin binding site on active. Myosin binds, get a cross bridge, get force production, maybe we get movement. We run the cross bridge cycle and the whole thing starts up. Okay. Every time you need to move, all of those steps happen. Thousands and thousands and thousands. Every time. Okay. All right. We will do a couple of neurotoxins when we start on Monday of next week. We will have a quiz on the lecture 4 on the control of production, also track stuff on Monday. Okay. If you got your assignment, please bring it up here and leave it with me. If you put it in on Canvas, great. If you email it to me, also great. We'll try to get them all graded and put up for you guys. Have a good weekend. We'll see you guys next week.
Okay, no worries, bud.